6G6Z3003 Dynamical Systems and Chaos, question number 6. Question 6a, we need to determine the critical points and stability of this two-dimensional system. And we're told that this is an interacting species model. We want to determine whether it's a predator-prey or an interacting or another type of species model. Part B is a Locker-Volterra model for a predator-prey. And we need to show that the Hamiltonian can be written in this form. Okay, so for 6 part A, we have a two-dimensional continuous system, so we need to determine how many critical points there are. So we use the solve command. And we get there are 4 critical points here. And you can see that they are all in the first quadrant, so that makes sense for a predator-prey model. Then we will need to work out the Jacobian matrix. So J is dp dx, dp dy, dq dx, dq dy. And now we need to substitute these values for O, A, B, and C into here to determine the stability of the critical points. You can see that you substitute x and y are both 0. Then here are the eigenvalues, 6 and 4, so this is an unstable node. We do the same for A, B, and C. And we get 2 saddle points, and the critical point C here is a stable focus. Okay, the isoclines are given by y is 6 minus 2x and y equals 4 plus x. So this is what the phase portrait should look like. So you have your 4 critical points, which are labelled here, and you can see everything is spiralling towards this stable critical point at x is 1, y is 5. Now physically, this is a predator-prey model because if you look at the equations, when x and y meet, you can see that this term here is negative. You have a minus xy, so the population of x goes down. So that means that y is your predator. Whereas here, in the y dot, we have plus xy, so the y gains from the interaction of x and y. So this is why this is a predator-prey model rather than a competing species model. If this was a competing species model, both of these terms here would be negative. But as you can see here, y gains from x meeting y. So this is a predator-prey model, and in this case, the species coexist. So in the long term, we settle down to x as a population of 1, y as a population of 5, and in the real world, these usually scaled by tens of thousands or hundreds of thousands. For question part B, we have a Locker-Volterra model. So here is our system, and if we set p is equal to log n and q is equal to log p, then 1 over n dn dt. So if we differentiate p with respect to t, we get dp by dt is 1 over n dn dt. So here is dp dt. And we know that p is equal to log n. So we substitute p is equal to log n and q is equal to log p. So we just substitute those values and we get these differential equations. And then we know that dp dt is dh dq and dq dt is minus dh dp. So then if we integrate our Hamiltonian, then we get h of p and q is equal to the expression given there. Yeah. So all that boils down to is p is equal to log n, so therefore dp by dt is 1 over n dn dt, and then we substitute p as log n, and we know that q is equal to log p. So the result follows. So this concludes the solutions to question number 6.